Hi, in this video I want to share a couple ideas and techniques on generating procedural layered rocks. We start with some kind of input geometry, base shape for our rock. First thing we need to do is generate some points we're going to use to cut along. So we start by adding a line node, and we need to center our line inside our rock shape. So first we set its length to be the height of the bounding box of the input shape. We do this with a simple hscript command bbox. Use the dy size as the last parameter, and then we need to center it because our input rock shape is not centered. So we use the centroid hscript command again, and we use the dx, y, and z parameters to specify the which component of the centroid vector are we interested. To center the line in the y, we need to offset it by the half of its length because it starts at the 0 and goes up. We offset it by using the same bbox command we used in the length parameter. Next we need to scatter some points on the line. We use the scatter node for it. Change the number of points, like to some 25 will be fine. But if all they're scattered quite uniformly around the line, so we just lower the relaxed iterations to leave them in more random order to make things more interesting. It looks like that some points might be too close to each other, and so we use the fuse node to merge the points which are too close together, so we can find some good value for the snap distance. Looks like 0.5 is fine. We just don't want layers to be too close together. And the final thing is we want to shrink the line a bit so the top and bottom points are not so close to the top and bottom of the rock shape. Just we don't need to cut there. So that looks good. So next thing, we just create a grid. We set its resolution to be 20 by 20 to have a bit more. Then we use copied points to clone the grid on each point. It looks like the grid is a bit too small for the rock, so we need to make it a bit bigger. 15 by 15 seems good size. Okay, let's add some random rotation to the grids to make things more visually interesting. So we do that by creating attribute randomize node. We set the distribution to orientation, and then we can set the direction for this normal attribute we're creating. Set it to pointing down, and just change the grid orientation to XY plane. Then we can lower the cone angle to some 2 or 3 degrees. Looks nice to have a bit of rotation, but not too much, so the grids are not self-intersecting. We can also add a bit of direction on x-axis to make them a bit more rotated, just to make things more interesting. Next, we want to add some noise to the grids, so we just create a mountain node. It looks a bit too much, so we can lower the height of the noise, also make it a bit bigger. Now we're ready to do the cutting. We do this with the Boolean node and change the operation to shatter, which basically cuts one object with another and leaves everything in place. We also want to enable one of the output groups, like this B inside A, because we'll use that later. So as you can see, our cuts are visible now. You can use divide node to just triangulate the polygons around cuts. This makes things even more easier to see. Okay, now we have our cuts, and we can use the for each connected piece loop to work on each layer separately. It automatically creates a connectivity node, which basically adds a unique attribute called class to each geometry island, like connected geometry piece. You can use single pass parameter on the for each loop to just check how each piece looks. You just add a new null node to name the piece, so it's easier to reference later when doing the actual work on the pieces. And we just add a normal node just to add the layers to the new faces. We use the point node because we'll want to smooth the normals, so we can do some expansion or shrinking of the layers later. Here we can see that we have this B inside A group on the newly created faces. Next we'll use that to add a little bit of erosion to the edges of the layers. So first we need to promote the group from primitives to points. As you can see all the points in this group. Then we use the new group expand node, which is new in the Houdini 18, to create new group based on the previous group. We'll just call it tops. We'll set the steps to -1 to actually shrink it, not expand it. So and then we'll use the group combine node to subtract the first group from the second, and therefore we'll get the border group, only points on the border of the layer along the cut. So we name the group border, and so it equals the B inside A group, and we subtract the tops group. So, and as you can see that now only these points on the edges are in this group. Okay, and next step is to create the point attribute based on this group. So we just use the attribute create node. Set it to operate on this new point group border, and name it also border. So basically what we want to have a value of 1 for points inside this group and 0 for the rest. We can just check it using the visualize tool. Looks fine. Next we use the polar reduce just to remove some of the small triangles along the edges. It also creates some kind of a random variation for each layer, so so there's some smaller gaps that start to appear. As it destroys some of the points on the border, as you can see, that just adds a bit more, even more random variation along the edge. Before blurring the geometry itself, we want to blur the attribute, so it's just more pronounced. So it's not just one pixel on one point on the edge, but also a bit more surrounding points. So we just use the attribute blur node to blur one iteration is fine. And then we use the same attribute blur node, but this time on the position. And let's rename the nodes just for easier. It's easier to find them later. yeah, now you can see that blurs everything, and you set the border attribute as a weight, so it now blurs only the points on the borders. This should kind of separate each layer from one another. You can see it by checking the single pass, see everything together, and yeah, it looks already much better. There seems to be some kind of strange artifacts produced. I'm not sure why. It turns out that the polar reduce merged some border points and produced values larger than 1. So to fix it, we just add a point triangle node and just clamp the border attribute to 0 and 1. Oops, mistake. So yeah, looks like it did the job. Next thing to make things more interesting, we want to add some random scaling to the layers. Not just like regular scaling, but actually more like an offset along a normal. So to do that, first we enable just one layer, so it's easier to work with. Then we add the normal attribute again to the points. Then we blur it. This way, when we kind of move our geometry along the normals, it moves everything more evenly and doesn't produce so much self-intersections in the crevices. So it's kind of more spherical. Then you add like a point triangle node. Let's rename nodes so it's easier later to find them. So first thing we need is to have a seed for a random function. We get it by using the class attribute that the connectivity produced. So basically for each rock layer, it has a unique value. So we can just use the prim.vex function to get it and use it as a seed in the random function. So we just reference the first primitive because they all have the same value. So we use it as a seed, and we can like add some user-defined seed just to be able to produce different results. We change the range of the random value to 0.5 to minus 0.5 to 0.5, so we can expand geometry on the positive negative direction. And then we just add this normal value multiplied by this random value and multiplied by the user input value, so we can change the direction where we offset the geometry. And let's see how it all looks together. You can see that it works. Some layers get bigger, some get smaller. Unfortunately, you can see that there are some gaps appearing between the layers because some of them are expanded in negative direction, so there are gaps are appearing. We can fix it by just checking if the random value is below like 0, and then we can just eliminate the y component of the normal, so it never gets kind of moved in y direction. And for positive values, we can just make it a bit smaller, so the rock layers expand more towards sides and less towards vertical direction. So it looks like it solved our problem with the gaps. Can just add a normal node at the end to see how it looks. in a more correct way. So yeah, looking good. Already some randomized layers, which seem a bit separated from one another. Some kind of erosion going on the edges. What we want to do next is add even more erosion, some kind of chipping of smaller pieces, like if the layers were cracked and some of the smaller pieces went missing. We start by adding back normals to our geometry. Just put back the single pass mode to work with one piece. Make some more room. Right, change it to points. And then we use the measure node to measure the curvature of the points. Change it to points and measure the curvature. Also, like, let's check the visualize of the curvature attribute to see what's going on. And we need to change it to the mean measure mode, because we want to measure separately concave and convex points, like produces different values. And then we use the add node and enable the delete geometry but keep the points to keep only the points of the geometry. And then using the blast node, we want to remove all the points whose curvature is less than a certain value. So we can type at curvature less 0.9 in a group, and it leaves just all the points whose curvature is larger than 0.9. Basically all the sharp points around the edges. We want to randomize it a bit more, so we just use the point wrangle node to add some kind of some random value to the curvature attribute. Basically reduce it randomly, so some points with the larger value now fall below the 0.0 value. You can use the point number as a seed for our random function. Change the range of the random value from -1 to 0 and add it to the curvature value. So now randomly some points get the smaller curvature and just leaves us with the fewer points. And it's good because we don't need that many points. You can play with it and see how it changes the end result. Next, we can create the Voronoi fracture node and use these points to cut the rock layer. Dot node to make it a bit easier to organize our nodes. Okay, enable the wireframe. So as we can see now, our geometry is cut, but the cuts go to the middle of the rock layer, and we don't want that. Let's add normal node so it's easier to see what's going on. So we use the extract centroid node to create a point in the middle of the rock layer geometry. Remove the piece attribute name, and you can see that there's now a point in the middle of the geometry. And then we can just merge the border points with this point and feed it into a Voronoi fracture node. And what it gives us, now we have like an island of geometry in the middle of the layer. Next thing we want to do is play a bit with the point positions. Basically, we want to offset them outside of the rock layer piece, as will change how the Voronoi fracture cuts up the piece. So we just first we calculate the kind of a normal vector, which is just like a spherical normal, which we calculate subtracting the centroid position from the point position. And then we just add it to the point position. Add user-controlled parameter that we can use to set how far apart the points should move. You can see, you can move them outside. Let's change the parameter range so we can also move them inside to -10 to 10. So we can move it further away or even inside. And what it gives is that if we move them further away, the inner island gets bigger and cuts are closer to the edges. So smaller pieces are being cut off. Then we use the awesome node called delete small parts, which is inside the game dev tools or now side effects labs since Houdini 18. And when we raise the threshold, we can see that now the smaller parts are removed. Let's see how it all looks together. Enable all the layers. And now you can see that each rock layer is chipped randomly, like there are some bits missing. We might want to add some more randomness to this threshold parameter, so some layers are more eroded and some less. We use the same class attribute. We reference the piece node in the beginning of the loop and use it as a seed for our random. We add like a base value of 2 and add random value multiplied by 2 to so basically have a random threshold between 2 and 4. Okay, and the last thing, we just add a null node at the end to identify that this is the Voronoi chipping method. Now I'll show you another method, basically similar, but instead of using Voronoi, we'll just use the Boolean shatter. So we just duplicate the node which offsets points, because for this method we need to offset points in the opposite direction, not outside but inside the layer. First move the points a little bit inside of the mesh. Okay, looks good. Next we just create a grid node, set its resolution to 40 by 40 to have a bit more details along the cuts. Copy to points. Right. Now the planes seem to be rotated randomly, so we want to correct it by adding a normal attribute manually to the points. You can use this spherical normal we used to move points, and we can also multiply the y component by some user value to give user ability to add variation, like more rotation. Let's change the range of the parameter. We need larger values. Then we add mountain node to add some noise to the cutting planes. Again, default values are a bit too high. I'm gonna make them smaller. Then we just use the Boolean node again, the same way as we did our initial cuts. And then we can use the same approach using the delete small parts node to remove some of the smaller pieces. Only this time we might probably want to lower the threshold value, so not so many pieces get removed. And now just add a null to identify this method as a Boolean chipping. can add a switch node, so we can easily switch between two methods. You can also, of course, use both methods in a chain, like first do the Boolean chipping and then do the Voronoi chipping on top of that. That's up to you. Let's see how it all looks together. It takes some time to calculate all the layers. Okay, looks like there are some strange errors. Something's missing. Weird. Okay, it turns out I just forgot to change the mode for the Boolean operation to shatter. As soon as I do that, everything should be fine. Yep, looks good. And this gives a bit different result as the Voronoi method, so just I wanted to show two approaches I found useful. Each might be useful in different kind of style of rock you want to produce. Voronoi is of course faster. And okay, so one last thing you can do to make your geometry watertight is to take the original input rock shape and scale it down a bit, and then just use the Boolean to union it with the new layer geometry. So it basically adds like a solid core to your new layers, just to be sure that there are no strange holes inside, unneeded gaps. We do this by adding point normal, blurring the normal, the same as we did with the layers. Then we can just move points along the blurred normal to smoothly scale it down. Do this with the point triangle. Just add in this case subtract the normal from the point position and add the user controlled parameter. Right, and now I just use Boolean to unify those geometries. And the last thing you can always do is just do a quick conversion back and forth to the VDB. This will just kind of heal all the self-intersecting parts or any weirdnesses in your geometry. Just a nice thing to do. Just set a small voxel size to not lose any details. Then convert back to polygons, and then just you can add like a polygon reduce node to restore a reasonable polygon count. You can use the continue reducing checkbox to like even reduce the flat planes even more. Okay, so this looks good. Just add the final null to identify the final output. Okay, the final thing I wanted to show you is like now we have all the layers are like distributed like quite randomly along the length of the rock. So what we can do is use more user-controlled point distribution method. For that I have like my own asset created that I'll share. And basically what it does is produces random points scattered along the user-controlled ramp. So we can specify the number of points we want, and then there's a ramp that controls the distribution of points. The node itself is very simple. It's just two nodes inside generate points, and then a bit of a vex code. And what it gives is just produces points in one position with a point attribute named scatter. And then you can use this attribute as you want to actually scatter them in some way. I do it by a simple point triangle. And for that I'll need a second input, because I need a bounding box in the center of this input geometry. So first I get the size of the rock geometry and the center position. Here's the first input because it's the second input. And then I just basically set the point y position as a multiply the scatter value by the y size of the rock mesh, and then we just offset everything with the center value and just subtract the half of the height of the rock from the center to move it down. Now connect the fuse to remove points that are too close to one another. And now we can use the ramp to control the distribution of the points, so we can probably have more points towards the top of the rock and less on the bottom. Kind of a artistic decision. Can have like two clumps of points. Here we may want to lower the fuse distance to have some layers even thinner. And now let's see how it all looks together. Okay, the cuts look nice. Sometimes the Houdini 18 doesn't refresh correctly the viewport. Okay, now it's good. Right, just like that, enable the last node to see how it all looks together. Takes a while to calculate. Alright, here you have it. User controllable layered rock. Just reduce the scaling of the layers a bit, it's too much. Okay, thank you for watching.